So now we have seen nucleophile, which is nucleus loving or affinity for the positive end. You can say electron rich species. So hydroxide, chloride, because they have extra electrons on them. So that's why we can call them nucleophile. So just to remember them, simply we represent like this Nu with the negative charge. So nucleophile can be negatively charged species like these, or it can be neutral molecule as well, which have extra electron on them, which can donate a pair of electron and make a dative bond. So in other words, we can also say that is electron pair donor, right? Electron pair donor to make the dative bond with the positive end. Now, as we are going to discuss the reactions which are nucleophilic substitution reaction. So when we talk about halogenoalkanes, their reactions are nucleophilic substitution reaction. And to remember them, let's me explain it in a simple way. For example, I have this molecule Rx. Rx represents halogenoalkane. As we know, R is basically alkyl group and X is any halogen atom. So let me take this simple example, CH3, which is a methyl group, which is bonded with the, let's say, Br, a halo group. So first of all, in this case, this pair of electron between carbon and this halogen, is it equally shared? No, it's not equally shared. Why? Because of the difference in electronegativity of bromine atom and the carbon atom. So due to difference in electronegativity, bromine has more electronegativity. So what we will observe, this pair of electron shifted towards bromine atom and it has partial negative charge and this carbon is partial positive. So in halogenoalkanes, we can say normally we have this polarity due to difference in electronegativity. So you can see there is partial positive and carbon and partial negatively bromide. So if any nucleophile comes near it like this, so we have already discussed what is nucleophile, which has attraction for the positive N. So in this molecule, which is halogenoalkane, so I can call it substrate. So substrate is a halogenoalkane molecule on which nucleophile attack. So, according to its nature, nucleophile that will definitely attack on this partial positive carbon. In this molecule, it has attraction for this positive end. And now we can see that carbon is already saturated, made four single bonds. So, to accommodate this new bond, what change we will observe, this pair of electron which is slightly away from carbon, that shifts to the bromine atom. And what we are going to observe, there is a substitution. The nucleophile will make a bond with the carbon. And which type of bond? Nucleophile is using its pair of electrons. So I can say it's a dative bond. Actually, arrow indicates a covalent bond, but coordinate covalent bond. And the bromine atom left as Br negative, right? So what we are observing in this simple reaction, that one nucleophile, this, that is substituting The another nucleophile, look at this, Br negative, that is also a nucleophile. Why? Because it has a negative charge. So you can say that one nucleophile is substituting the another nucleophile. So we use special terms for them. Now, this one, which is coming on into this molecule or which is attacking on the substrate, we call it attacking group. That is attacking nucleophile, right? Or you can say attacking group. And this nucleophile, which is leaving the molecule, that is our leaving group, right? And the product which we got, that is our main product, substitution product. So, attacking group, leaving group, and substrate and product. So, what we will observe in these reactions, that one nucleophile will substitute the another nucleophile. So that's why these reactions are known as nucleophilic substitution reaction, right? Nucleophilic substitution reactions. Is it clear? And next, these nucleophilic substitution reactions, we can classify these nucleophilic substitution reactions into two categories. First of all, I am going to represent this term nucleophilic substitution as S and N. Actually, S stands for substitution and N stands for nucleophilic. So, nucleophilic substitution is represented by SN. And there are two types of these nucleophilic substitution reactions. One is SN2 and the another one is SN1. So let's see what's the difference between SN2 and SN1. So to understand these two types of reactions, let's see first of all the classification of halogenoalkanes. So we have primary halogenoalkanes. So what are actually primary halogenoalkane? Those alkanes in which the carbon which is bonded with the halogen group, that is further bonded with only one alkyl group, right? Or the carbon which is bonded with the halogen, let's say, which is not bonded with any other alkyl group. So all these are primary halogenoalkanes and we represent them with one dot. That is basically primary halogenoalkanes. Now, primary halogenoalkanes have a very unique property that whenever they react with a nucleophile, let's take the nucleophile OH negative. When this nucleophile, as I said earlier, this will be our substrate molecule, halogenoalkane, on which this nucleophile attacks. And this will attack on partial positive carbon right here. And this pair of electron, which was shared between carbon and chlorine, that will go to the chlorine atom. And remember one thing, the direction of arrows is very important. As I have already told you, we draw the arrows from negative end towards the positive end. As you can see here, this is shifting of electron. And remember one thing here, it's a complete arrow that shows heterolytic fission. Heterolytic fission in which the bond breaks and pair of electron goes to one atom. So it's heterolytic fission. Clear? During this reaction, we get an intermediate in which I can show like this. Intermediate dotted lines Cl and dotted lines OH. That is my intermediate. What is basically intermediate showing me in this reaction? Actually, these dotted lines, they indicate that the previous bond is breaking. You can say that is breaking the previous bond, and this is forming. And in this case, intermediate, when we represent, you can see neither the previous bond nor the new bond is completely formed or broken. So that's why we are showing them with the dotted lines. So in this case, we can say that the extent of bond breaking is equal to the extent of bond formation. So if 50% of the previous bond is broken, that means 50% of the new bond has formed. And next, when this previous bond completely breaks, the new bond will 100% form and we get this substituted product like this. And a leaving group, Cl negative. So as you can see in this reaction, the main property of this reaction is taking place in a single step. That is a single step reaction. Single step means that both the bond formation and the bond breakage, they are occurring simultaneously. That's why I said the extent of bond formation and extent of bond breakage, they are equal. So as the previous bond breaks, the new bonds will form. So even if I represent these type of reactions, so energy profile diagram will be like this. Let's say it's if exothermic reaction, so the reactants here and the products here, and that is the point where we have intermediate, right? Here. So it's a single step reaction in which both the bond formation and bond breakage occur simultaneously. That is very important property of this reaction. And remember, this reaction is shown by which halogenoalkanes? We are talking about primary halogenoalkanes. Now, next important thing, when any reaction which takes place in a single step, when we talk about the rate of reaction, so we write down its rate equation, right? So remember, we derive the rate equation from experimental data. And for these reactions, which depend on a single step, that single step is also known as their rate determining step, right? That is rate determining step means the rate of reaction is determined by this single step. So the rate equation for these type of reactions, which are single step reactions, will be equal to rate constant K into concentration of reactants. So how many reactants we have in this reaction? So we have alkyl halogenoalkane and we have attacking nucleophile. You can say in this case, specifically Rx, that we took chloromethane, right? So that was our substrate. And this hydroxide, that was our attacking group. So in this reaction, you can see the rate equation will be rate of reaction that is equal to rate. K is actually rate constant, right? Concentration of this chloromethane and concentration of our attacking group. And you can see in this reaction their number of moles. There are 1 mole and 1 mole. So in our rate equation, we have here 1 and 1. So concentration of chloromethane raised to power 1 and concentration of hydroxide raised to power 1. Now here one new concept which is called order of reaction, right? Actually, what is order of reaction? Order of reaction is the sum of exponents in rate equation. Remember, in rate equation, that is called order of reaction. So in this case, these are the exponents. So when we add these exponents, so what we got here, 2. So order of reaction here for this particular reaction, so its order is 1 plus 1, 2. It means this reaction is second order. So these nucleophilic substitution reactions in which the order of reaction is 2, we represent them as SN2 reactions. So these reactions are basically SN2. Why? Because these are nucleophilic substitution reactions and their order is 2. And here, one more definition which is very important, that is known as molecularity, right? Okay, what is actually molecularity? Molecularity means the number of molecules of reactants in rate determining step, right? In rate determining steps, actually, that is known as molecularity. So in this reaction, you can see how many molecules they are participating. We have one molecule of this halogenoalkane and another molecule of this attacking group, which is hydroxide. So here we can say this reaction is bimolecular. Why? Because two molecules are participating in our rate equation, you can say, which is based on this rate determining step, right? So its molecularity is 2 in this case. So that's why it is also known as SN2 reaction. Why? Because it is bimolecular. So SN2 then stands for what? We can say nucleophilic substitution bimolecular reaction. Why we are calling it bimolecular? Because two molecules, they are participating in rate determining step. And remember, it is very important, rate determining step. Order of reaction. What is rate determining step? The step which is used to write down the rate equation. And remember, this reaction is only single step reaction because both bond formation and bond breakage, they occur simultaneously. So it's a single step. So if reaction is a single step, then that single step will also considered as its rate determining step. Is it clear? So primary halogenoalkanes, they follow this SN2 reaction mechanism. So let me revise again what is actually SN2 means. So SN stands for nucleophilic substitution, and Y2, actually this 2 indicates here, that indicates it's a bimolecular reaction. Why we are calling it bimolecular? Because its molecularity is 2. Now what is molecularity? The number of molecules which are participating in our rate determining step. So if it's a single step, then this will also be the rate determining step. Is it clear? And primary halogenoalkanes, they follow SN2 reaction mechanism. Next, rate equation, which is derived on experimental data. Rate is equal to K. K is basically rate constant, is equal to concentration of substrate raised to power 1 and concentration of attacking group raised to power 1. So order of reaction is the sum of exponents in our rate equation. So its order is 2. So that's why it is also known as SN2 reaction mechanism. Is it clear? Now let's see some of the details of these nucleophilic substitution reactions from this example. Look at this. The signature of halogenoalkane is nucleophilic substitution reactions. So substitution of an atom by a nucleophile. So what is nucleophile? As I told you earlier, nucleus loving, which have affinity for the positive N, or which is electron rich, or you can say electron donor. So here in this example, as you can see, the Cn negative, that is behaving as a nucleophile, OH negative with extra electron, water, oxygen has lone pairs, so this can behave as a nucleophile, ammonia, nitrogen has lone pairs, so this can also behave as a nucleophile. So nucleophile is a species which can be an ion or which can be, and remember, it can be either negatively charged, right? It can be either negatively charged or it can be neutral, as we can see from our examples, right? Which is strongly attracted to a region of positive charge in something else. For example, it normally carries either a partially or fully negative charge on a molecule, as we saw in these examples. Is it clear? So now, next, what is basically these nucleophilic substitution reactions means? So nucleophilic substitution is possible due to the polarity of carbon halogen bond. As I explained earlier, the bond between carbon and halogen, it's polar because of the difference in electronegativity. So halogens are more electronegative than carbon. So electron pair will shift little bit towards halogen atoms. right? So that's why they carry partial negative charge and carbon as a partial positive charge. Okay, so here one more term I want to introduce. This carbon, which is having a positive charge on it in halogenoalkanes, so on which nucleophile attack, right? So this positively charged and that is actually known as electrophilic center. I am calling it electrophilic center. Now, as I introduced to you the nucleophile, the here another term which is opposite of nucleophile, that is electrophile. So what is electrophile? That is electron loving. Is it clear? Or you can say I can represent is E positive. It can be partial positive, it can be completely positive. So you can say electron deficient, it can be, right? So electrophile is electron deficient, can be partial positively charged or completely positively charged. So here in halogenoalkanes, the carbon with partial positive charge, that is our electrophilic center. Got it? Okay. So nucleophile is attracted towards this positive center and carbon iodine bond, although there is no polarity, it is still possible. So what does it mean? Actually, when we move down, so what we are observing in the bond polarity, actually, while moving down in halogens, you can see their electronegativity decrease. So it means that the bond between carbon and fluorine that is most polar. Then carbon chlorine is even less polar, bromine is less polar than that, and the least polar bond is carbon iodine. So we can say almost same polarity. If almost same polarity, that means this bond will behave as non-polar. Why? Because electronegativity difference of carbon and iodine is very small. So here there is no polarity, but it is still possible because nucleophile can induce a dipole in the bond. So when nucleophile approaches this molecule, so it shifts this pair of electron towards iodine. So that means it induces the dipole due to repulsion of the electrons of nucleophile and these electrons, right? So that is also possible in case of alkanes. Now, as I explained earlier, there are two types of nucleophilic substitution reaction, SN2 and SN1, and we have done SN2, which are shown by the primary halogenoalkanes. SN2 mechanism, the main property of these SN2, that is a single step reaction. Is it clear? And during this, what we get an intermediate. So, and then we get the final product. So I used the special terms. So here you can see in detail, S stands for substitution, N stands for nucleophilic, and 2, that stands for the order of reaction or the molecularity. What is molecularity? The number of molecules which are participating in the rate determining step. So look at this. 2 stands for initial step, which is rate determining step, involves 2 species. So 2 molecules. One of them is halogenoalkane and the another one is attacking nucleophile. Clear? So the general mechanism of SN2 They are using ethyl bromide. I used methyl bromide, or you can say bromomethane or bromoethane. Here it's a bromoethane. I used uh, chloromethane as an example. So any primary halogenoalkane can be used as an example. So what will happen? The nucleophile will attack on partial positive carbon. So Br will leave and nucleophile will take its position in this molecule, right? So the carbon bromine bond is polarized due to electronegativity difference. Here I can show this bond, carbon and bromine. So partial positive, partial negative, like this, right? A nucleophile that can be OH negative, that can be CN negative, that will attack on partial positive and which is carbon. Nucleophile attack towards the positive carbon, and I can also name this positive carbon as electrophilic center. Is it clear? So, what happens? Coordinate bond will form between nucleophile and carbon. As I mentioned, the bond between a nucleophile and carbon is coordinate bond. Coordinate bond means dative bond. The pair of electron is given by the nucleophile. Why? Because this pair shifts to the leaving group, which is bromidine. So during this transition state, which I used the word intermediate in my explanation, and then after that, we will get the final product. Clear? So here you can see where the carbon bromine bond is just at the point of breaking and the carbon nucleophile bond is just at the point of forming. So transition state has 5 groups attached to the central carbon atom. So which 5 groups? Look at this. If I draw in this case, the transition state will be like this: bromine, nucleophile, hydrogen, hydrogen, and this methyl group. So how many groups are attached with this central carbon? 1, 2, 3, 4, and 5. It's an intermediate in this particular case, where we are using bromoethane as an example. Is it clear? So now next, what we get after the substitution final product will be CH2 and nucleophile and CH3 and Br negative. Is it clear?